Right, so this is our last meeting at the Cinco de Mayo. All right, so the test 3 is Wednesday a week, but it starts at 4 instead of our usual 3:30 time. It's a longer period of time than our usual time. Sort of, I think we go to like, I don't know, 5:45 or something. Okay. I want on the last day to look at the syllabus. It's a good day to look at the syllabus, the last day. And I want to remind you of how this grade is going to be calculated. So there's going to be, I don't know, test 1, test 2, and test 3. And I just put in some fake grades of 70s. Then there's a homework grade. That's not 10 on the test. Nobody would get a 10 on the test, 70. Let's say you were good and did all the homework, so that's 100. The class, everybody will get 100. And the lab, nobody gets 100, but people get, I don't know, 98. And then the overall average is going to be, each test is, the tests altogether are 60 and there's 3, so that's 20%. So I can either do a test average and give it 60%, or I can give each test 20%. So what I'll do, test 1, test 2, and test 3 are all 20%. And then the homework was 10%. What am I doing? 0.10, 10% times a homework grade plus a class grade is 5%, 0.05 times a class grade. And then a 0.25. I screwed something up because this. All right, what did I do wrong? 0.2 times A plus B2, C2, that's the tests, plus 10% times D2, 0.05 times E2, and 0.25 times F. Okay, so it did some kind of fixing for me. So that is 370s, did most of the homework, and then you end up with an 80. That doesn't. So this was 60% was in the 70s. The other 40% was in the near 100. All right. What are you asking me? This year, we are going to have a chance to change our grade to a neutral straight like last year. I have no idea. I have not heard that. The announcements that we were doing that in the past have occurred much earlier than this. So my guess is no, but I haven't heard that. I haven't heard that they're doing it. I haven't heard that they're not doing it. I just simply haven't heard. So, so just checking my calculation one more time. 20% for each test, 10% for homework, 5% for class, 25% for lab. and then you put it on this scale. So this person, I usually round up. And so this person who is getting all 70s can get a B minus. That's if the homework in the class, everybody gets the 100, but the homework and the labs have to be in for that. If you get everything in, but everything was late, you just did everything late, then these usually get 90s. Now you're down, getting the same test scores, but doing everything late. Still a lot for late, but that then now you're down into like the C range. And then if you start to can't bring yourself to turn in all the labs, not turning in all the homework, now we're getting down into the worrying range. We still, okay. So I will, this is going to the homework's not a lot, but it's 10%, which is a full grade. And the lab is 25%. And there's no reason for them to be that low. And so even if you were getting, I don't know, 54s on the test, that's a pretty low score, but that happens. Even if you're doing that, if you had very low test scores, but and late homework and late labs, you can still get through this course. But it's a disaster if you don't turn in the labs. So that's all I want to say, but I want to sort of prove it to you numerically, that you can do, that's a fairly low test score. I mean, some people do that poorly, but some people just don't get electronics, and that's okay. But if you sort of work hard and do most of your work on time, then we can get, even if you do poorly, we can get you some kind of grade that gets you the credits and gets you through. That's where the goal for some people is to get an A, and the goal for other people is just to get through. So do your homework, do your labs. You should be able to get through. Okay. And there shouldn't be any mystery. This is how the grade is calculated. Okay, and you have a recording of me calculating the grade, so you can model yourself after this and calculate your own grade when this is done. Okay. Now as we say, we have one test. There are labs and homework that some people still have to turn in. I am in my grading, I'm on, I think, Saturday. I gave a test in another class on Monday, so I'm probably not going to get, I'm going to really slow down when I get to Monday in my grading. So I can probably get through Saturday and Sunday. So if you send me something Saturday or Sunday, there's a good chance you'll get some response from me. If you've turned it in after Monday, things are really going to slow down. There'll be a slower turnaround. So you really, if you have a question, then you really need to ask it. You can ask it here in class today, or you can ask it in a more private fashion. But if you have a question to ask, don't just assume I'm going to get to your lab and see what you did wrong and tell you how to fix it before the test. You need to be a little more proactive. Okay, and just we've done this more than at least twice already, but on this test is 9, 10, 11, 12. 9 was flip-flops, RS flip-flops, JK flip-flops and counting. There was a little slideshow on hardware generations, which may pull some little fill in the blank question for, or matching, or true, false, or something or other. We talked about transistors, them being on and off, and we've talked about using transistors to make logic gates. In 10, we've added our transistor to our capacitor and made DRAM. We've talked about a digital comparator, and then we started talking about architecture and mapping out the micro instructions. So you know you're going to get one of those map out instructions, because I keep telling you you should get it at least half right. So you know you're getting one of those on the test. I could ask, have some kind of fill in the blank kind of question where I describe the program counter and you have to fill it in and tell me it's the program counter, something like that. So you're supposed to understand the roles of the things in the architecture. So what's an instruction register? What's the accumulator? What's the memory address register? Then in unit 11, we had a circuit that was a RAM circuit. So we added a bunch of registers to a decoder. And so you have to know how to address the, so there are switches for the addresses, there are switches for the data, there are switches for writing and reading. And so I will say to write and then read some value at some particular address. Okay, and you better have the decoder tells you this is 0, 1, 2, 3. So you better agree with the decoder. So if I say 2, then that's determined by your decoder circuit. So you better agree, 0's 2 lows and 3 is 2 highs, but 0, 0, 1 and 1, 0, 1 and 2 can possibly be confused. And you're supposed to make sure you get the same one. So I recommend putting some little probes on those lines to see that the appropriate one is sort of lit up. So, but that's, so you already have the RAM circuit in lab 11C. You're supposed to have figured out how to work the RAM circuit. And so you're expecting on the test for me to tell you, here is the, here's the data I want written to the address that I want written. And if you've learned what you're supposed to learn here, then that should be easy points. You have to give me a screen capture. I tell you to send me other circuits. Some of you never send me any other circuits, but I usually want you to send me other circuits. But for a circuit like RAM, which is memory, which is volatile, you really need to send it, show me a screen capture of it working. It's not just, certain logic circuits, if I open them up, I can see, oh, you know what you're doing or you don't know what you're doing. This one is very history dependent. Did you click the right buttons in the right order? Okay, so you're expecting a RAM circuit. In 11A was those in circuits with inductors. And so you're expecting probably one of each of those. And 11B, I think, was stacks. And again, it was mapping out one of those instructions. And then 12 was just the fun making a sign. So this is just, so we've gone over everything and I'm just sort of reviewing and answering questions. I have in mind that I should probably review an LC circuit and an RL circuit, because I know they're on the test. And but I want to ask if you guys have any questions before I go doing that. I'm looking in the room if there are questions. I'm waiting for any chats to appear. I have a chat appearing. Okay. Can you show the RAM? Okay, I can show the RAM. I think I have it I may have it unzipped somewhere. If not, I will download it and unzip it again. I do have it there. RAM. Do I have it? No, I don't see it. I see capital R, I don't see. All right, I will download it then. So you should get yourself organized before Wednesday, and when you are using, again, anybody who, if the university hasn't designated you as a pariah who's not allowed on campus because you haven't had a test, if you've had the kind of test that allows you to come to campus, you're allowed to come to campus to take this test. I find it easier to use that software at a computer than it's installed on, but you can use the remote version. And if you haven't, there is like a temporary version you can download. Just make sure you don't use, I don't know how many days it gives you, but if you haven't used it already, you might have it, install it and use it, get through the test with it. But anyway, what else did I want to say? I'm rambling and rambling. When you're using the remote system, you have to know sort of where the things are and how to access them. So the RAM circuit is something you already have. I probably won't give it to you again on that day. I've already given it to you. But the LR circuit and the LC circuit and the RL circuit will be a new circuit, so I will give them to you. Now you're allowed to take the circuit. I'll also have a picture of it in the Word document. So you're allowed to take the circuit you already have and modify it to what I have, or you can use the version I give you. But you just have to know, like if I give you a zip file, if you download a zip file, say from my web page and unzip it, then how do you get that to where you can work with it with the remote system? That's something you're supposed to know. Like I just clicked on the file and it opened up in multisim. When you're working remotely, your computer doesn't have multisim installed. It doesn't know how to open a multisim file. So you have to sort of open multisim and then go find the file. So you have to work sort of opposite of what I've just done. And you're supposed to know that. But I find at least one question during each test where people don't quite seem to know what to do with the files I give them. Okay, so he asked how to run the circuit. So first, first unzip it. Then I have to say, let's just say I'm going to put in whatever it's set up to be right now. That's what I'm going to put in. So I'm going to put in, this is high, low, high, low. So that's 1, 0, 1, 0. That'll be a 10, which is an A. The A is high and the B is low. That's the thing you got to watch out for. So I'm going to do what I just suggested. I'm going to put some probes on here. Come on, probe. probe, probe, and probe. Okay, that's enough probes. All right, turn the sucker on, okay. And now I am at address. Let me turn it off for a second and blow this up. View, I'm going to zoom in. Okay, so this is labeled here. Zoom in one more time. This is labeled here 0, 1, 2, 3. You've got to live with those addresses. So right now, and this gives you with these little circles, sort of gives you the opposite of what you sort of normally want. That's why I put it back through an inverter. And so it makes one of them high. We're picking one of them, and we're picking here. This is 0, 1, 2, 3. So this is the address 1. Now let me go zoom out again. Okay, so this was address 1. And so I'm going to put, I think we're expecting, so this was address 1, and I'm going to expect this to be a 10, but I have to write it, and write means I have to go through an edge. So I'm going to take this W switch here and go back and forth. Of course, I didn't turn it on, turn it on. Okay, and then go back and forth with the W, because it's writing on the edge. And I'm reading, so I can see what I wrote. If I'm not reading, I see a 0, but I want to read. So R high is reading. W to write, you have to go back and forth through a clock cycle. The A and the B determine where. Right now I'm writing to address 1. And the 3, 2, 1, 0 are the 8s, 4s, 2s, and 1s place of the number. Since I was high, low, that was a 10. Which is an A because it's hex. If I tell you to write a number, and then you can put it in the calculator and put the calculator in hex mode and put the number in the calculator and get the binary for it. And, you know, if you know the binary, fine. If you don't know the binary, you can use the calculator. Or what does A and B do? A and B are the address. So there are 4 4-bit registers. Here's the register at address 0. Here's the register at address 1, the register at address 2, the register at address 3. So the A and the B determine which register I am working with. So I wrote to and then read from address 1. And so A must be the 1's place and B the 2's place. And so with A high and B low, I picked out address 1, and that's what I wrote to. So the AB is the address, that's the where. I am going to tell you, I want something, some value. The some value is the 3210 at some location. The location is the A and the B. And nothing works unless you understand about edges and to go through the W back and forth. Then because this is history dependent, that you have to go through the edge and all that kind of stuff, you must give me a screen cap. Can't just give me my RAM circuit back and have me sort of say, oh yeah, you know what you're doing. If you know what you're doing, you realize it's a memory circuit, it's a volatile circuit, and you have to show me it while it had energy, while it was working. So you have to show me things lit up. Questions? there will be a question where I will say, write this value to that location. So please know it's coming, please get it right. All right. Somebody turned in a lab 10 with, they turned it in a little bit early before I gave all the answers, but they did the one instruction. This was the part of 10 that has the mapping of the instructions. I gave the first instruction, I gave the load, and they gave me what I gave them. Give that to me, correct? And then for the second one, I told them that they, you should get it at least half right, and that's what they did. They got it half right, and not they got it half right because they tried and they made a mistake. They didn't even try. And I'm telling you, not even trying is a mistake, because if you play around with these things, you'll get to understand them. But even if you don't understand them at all, if it's blank, it's wrong. If you just accidentally get one of the, I say, who's driving the bus, and you say the MDR, you might get lucky. You might get another point or two out of it, just for being willing to try. I don't take off points. I don't take off away points when you're wrong. I give them to you when you're right. So guess. All right. All right. And I said I wanted to show you another RL and LC. So let me find those. I already have some somewhere, probably in documents. Here is an LC. Let's look at the LC. So here is some LC circuit. Let's change the numbers. You've got to, so I'll probably give you this circuit and then you have to run it. So I'll change the resistance to, I don't know, 2.38. Sounds like a good resistance. I'll change the capacitance to 5.4 microfarads. I'll change the inductor to what do I want? 440 millihenries. Sounds good. All right. So there is some values, and I'm going to open the oscilloscope, and I am going to start the circuit. I'm going to click in the space. I'm going to hit the space bar to move this up. I'm going to hit the space bar to move this down, and then I'm going to turn it off. Okay. So here is when, before I flip the switch. I was really slow on that. Then here is this rise. That's when the switch was up, and we're getting an RC circuit. So this is just a charging RC circuit. Now, let's say you saw something like this, and it's taking too long. Then you play with this time division thing. So now I moved it from 2 milliseconds per division to 5 milliseconds per division, and now I see more of this charging. In this particular circuit, I'm not really interested in the charging part, but I just want to remind you, that's my whole purpose for this right now, is to remind you that there's this the scale setting that you can change. There's also this, so that changes things horizontally, bunches it up. So now I'm seeing, so I can stretch it out, or I can sort of compress it. And then, but what we're really interested in is this repeating behavior over here. And let me spread that out a little bit. Maybe one more. And then scroll over to it. And we want a period. I usually go from a high to a high. So there's a high, there's sort of a high. You just need to get it basically right. Then you'll give me this as like a screen capture. I'll say, what's, simulate the circuit, give me the simulated period, and give me a screen capture. So you'll give me the screen capture. I'll use the snippy thing. And you have these needles, and then down here, that time difference, there is, so there's me indicating, so either you can type out on the, you can type it out on your page. Here is the number I took off the oscilloscope, or so you can fill in the box with it, or you can circle it or somehow indicate like I know the answer. Okay, so there is the oscilloscope reading, us measuring the period. It's the time to repeat, so you can go from low to low or high to high. You can go from 0 and heading up to the next 0 and heading up. Those are all versions of the period. I usually do high to high. Okay, so that is the theoretical period. Then I'll ask for the frequency. I'm just going to bring up this calculator. The frequency is 1 on the period. I'm going to be in scientific mode, and I'm going to say 9.689, and then I'm going to do a 1 on. So there is my frequency, 1.103, and I have, to do that calculation, I had milliseconds in the denominator. So when I get the frequency, it's going to be kilohertz. So this is kilohertz, 0.103 kilohertz, or I could say it's 103 hertz. You can choose what unit you want to give me. Well, you can't give me some crazy made up unit, but you can choose whether you want to report your answer in milliseconds or seconds, and whether you want to report your answer in hertz or kilohertz. So I was reporting the answer in milliseconds and kilohertz, but that's up to you. So long as your number and your unit are correct, I can figure it out. I can, so I'm not going to specify that the answer must be in seconds or milliseconds or what have you. So that is the simulation part of it. Run the oscilloscope, turn on the circuit, operate the circuit with the switch, find the right, measure the right thing you want on the oscilloscope, and that's going to get you a period. From the period, calculate the frequency. You should know how to go from periods to frequency. I might just give you a problem that says, here's a period, tell me the frequency. So you should understand how to do it in the context of this problem, but you should also understand it, if I ask it someplace else, you should understand that it's the simple reciprocal calculation. Can you show another demonstration of calculate the frequency. So let me change the values. I'll change the values. And I'll repeat it. Okay. So what do I want to do? Properties, I'll change this to 90 millihenries. And what am I going to do with this? I'll change it to 4.5. Okay. So I'm going to open that up. I'm going to, again, run the circuit. I'm going to flip the simulation on. I'm going to click in the space. I'm going to hit my space bar up. I'm going to hit my space bar, put this switch back down, and then I'm going to turn the circuit off. So on, in the space, 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 and off. Okay. So here is, this is the RC part. We're not interested in the RC part. That was test 2, but that's what this is. And now here's the repeating part. We're interested in the period. So I can measure a period, or I can, maybe I'll stretch it out. And then I'll have a more accurate, if I stretch it out a bit, I'll have probably a more accurate period. So here's from a high to the next high. That is a period, and it was 4.048 milliseconds. I go to my calculator. I can work in these units. I'll also show you in a second how to work in other units, but there is 4. So you can do, I can do 1 divided by 4.048 to get 0.247, or I can say 4.0481 on. Those are the same thing, but just different ways. So I did it the reciprocal way the last time, but you can also just do your own reciprocal by saying 1 divided by. And so the answer here is 0.247. And I was working with milliseconds. And the thing that goes with milliseconds, because this is thousandths of a second, the frequency that goes with milliseconds is kilohertz, thousands of hertz. And so it's 0.247 kilohertz. Or you could say, I don't like millis and I don't like kilos. Then you have to convert. And then you would say 4.048 milliseconds is 0.004048. So I could say 1 divided by 0.004048. And then I get 247, but now my answer is in hertz. So I know there are people who don't like millis and kilos, and so they like to convert and get rid of those things. And that's fine, you can do that. So it is just a reciprocal. So you can use the reciprocal button, or you can do the 1 divide by yourself. You can work in the units that as they come up and understand what units, the corresponding units you get when you do a reciprocal, or you can convert to the main unit of seconds, and then you will get an answer in hertz. But this is the simulational frequency. So this was the simulational period. And then if you take the reciprocal of it, it's the simulation frequency. And then I will ask you for the theoretical frequency. So I have a calculation, and I show you how to do that calculation in Excel. If you like calculators and you have to take a square root and the reciprocal and yada, yada, yada. If you like that, if you're happy with that, if you're, on your calculator all the time, then by all means, you can just use your calculator. But I show people who haven't played with a calculator in a while how to do it in Excel. And then if you get it set up right in Excel, then you don't have to do the calculation again. All you have to do is update the data appropriately. So let me show you that. So where were we? 11A. And we're down here. And I'm telling you, here's how to do this. Now here in the Excel calculation, I am working in the base unit of everything. Okay, I probably have the Excel saved somewhere, but maybe I do, maybe I don't. I'm not seeing any Excel saved here, so I'll just make it again. But come in prepared. Come in, you know, if you like the Excel approach, then come in prepared and have the Excel spreadsheet ready to go. Then all you're going to have to do is change the numbers. So there's a place for L, and that's going to be in henries. So it's the base unit. There's the capacitance that comes in farads. And then we're going to get a frequency, and that's going to come in hertz. Okay, so let's first get this example right, and then we'll change the values to what we were working with. So this was 1 millihenry, and then I converted it to henry, so that was 0.001. Why do I have a comma? And then this was 1 microfarad, so that's point and then 5 zeros and a 1. 0.1, 2, 3, 4, 5, and 1. Okay, so again, I'm working in the base units, henries and farads. And then I'm going to do this calculation of equals 1 divided by, everything's in the denominator, so I'll take a set of parentheses, 2 times pi. In Excel is this weird PI open close parenthesis. They made it a function. If that drives you crazy and you hate it, pi is 3.14, good enough for me. Don't tell my mathematician friends. All right, but I'll do it the proper way and say pi. Okay, it's not case sensitive, Excel. And then we need the square root of L times C. That's the close of the square root. That's the close of the denominator. And there is that answer. So first try to duplicate what I have if you're taking the Excel approach. Now let's adapt it to what I'm currently running. So my inductor was not 1 millihenry, but 9. So if I were going to convert this to henries, the dot right now is after the 90. I moved the decimal place 3 times, so it'll be 0.09. I have 45 microfarads. Micro is 10 to the minus 6. I'm going to move the decimal place 6 times. I'm going to move it from here to in front of the 4. That's 1. And then I'm going to need it 5 more. So it's going to be 0.5 zeros and then 4 5. 0.1 2 3 4 5 4 5. And then here is my frequency, my theoretical frequency of 250. Here was my simulational frequency of 247. Not half bad. There's one of them on the test. If I'm feeling evil, what would I do? I'd put another capacitor here in series, or I'd put another capacitor here in parallel. That's me at my meanest on this circuit. Questions? All right, let's look at the RL. This is the harder one. The RL is usually easier. So here's the RL. Sometimes I call it LR, sometimes I call it RL. I don't know. I'm dyslexic. What can I say? All right. So let's pick and some inductor, just making it up. I'll say 220. Capacitors in series and parallel are the opposite of resistors. Yes. So if let me go back. So if I put, so I say if I were being mean, so let me be mean. If I were to do this, let me rotate it. Then this is parallel. That's parallel. And so is that. There's no difference there. If they were in parallel, capacitors in parallel add. So instead of being 4.5, it would be 5.5. If I were even meaner, I would put them in series because capacitors in series add reciprocally. And then you would say, let me change this from 1 to, because I don't want to take the reciprocal of 1, because the reciprocal of 1 is 1, 2.2. Okay. So if I were to do this, I would say, oh, it's scrolling on me. Stop scrolling. Okay. Stop. I said stop scrolling, so stop scrolling. All right. Mother of God, stay there. Oh, there. Now we're coming back. Okay. So I would say 4.51 on plus 2.21 on equals, and then another 1 on. So you should have 3 1-ons. In the reciprocal formula, there are three reciprocals in the reciprocal formula. 4.5 1-on plus 2.2 1-on equal to perform the addition, and then a final 1-on. And then you would work with this in the theory. You would work with this equivalent capacitance. So that's me at my meanest. Resistors in series or in parallel in this circuit. I might do it for the LR, or I might do it for the LC. If I do it for the LC, it's capacitors. If I do it for the RL, it's resistors. So now that I told you it might be coming, it shouldn't be much of a surprise, but okay. So here is, I changed these values. I think I changed the 220, but I didn't change the R yet. Okay. I'm going to change this to, I don't know, 3.33. Okay. So again, we're going to run the simulation part, get the simulation part. I'm going to, let me tell you about the meanest thing I could do here is something else, me at my meanest. Yeah, me at my meanest, okay. Because there could be something, here's the circuit when it's going up, it's got the 220 and the 3.33. It's got L1 and R1 and the battery when it's going up. And then when it's going down, it's got the L1, R1, and R2. So it can be, the ones we did for lab, they were the same going up as going down. That it can be different in the going up and the going down circuit. Again, that's at my absolute meanest, that's what I can do to you on the day of the test. But if you go through the motions and you miss my one little trick, you'll still do pretty well if you know your basics. You know, I'll throw in 1 point for something like this, and you lost 1 point if you got all your basics right. Okay. So again, this is turn it on, click into the space, flip the switch, turn it off. On, space, flip. There. Okay. All right. I have multisim 13 instead of 14. Is that okay? If you have a circuit like this built and then I give you one, then you're going to have to modify yours rather than use mine. If you gave me a 13, I can run it using 14. But if I give you a 14, you can't run it using 13. So this circuit's going to be like this. It's not like the resistor network or the capacitor network where it's going to be some big crazy convoluted thing. It's going to be basically this setup. So if you have it built in 13, you're not going to be able to use mine because I'll probably hand you a 14. Because what I have right now is 14, and if I touch anything with 14, it turns into 14. They used to be able to like save as an old version, but they don't do that anymore. So if I touch anything with a 14, it becomes a 14. So what I'm going to give you is going to be a 14. So then the problem becomes, so you're going to have to instead modify your 13 version to become my version. So you just have to watch the units. Usually it's just a change in the number, but just make sure there aren't any funny units. That there's, this is millihenries and this is kilohertz. If you remind me, because of this problem, I will not remember, but I think I have a RAM. I think I have an old RAM that might be older. Because if you're trying to work your RAM, my RAM is 14, and that could be a problem. And that's a complicated circuit. You don't want to be building RAM during the test. This circuit's easily modified. So you might be saving time by not working remotely, but you're going to have to change the values rather than work with the circuit I give you. So, and that's fine, I don't care. And as I say, if you send me a 13, I can run it. The circuit that's complicated that I'm going to make you work with is the RAM circuit. That's the one that's not easy to build. So you've got to make sure, if you're going to work with 13, you have to make sure you have a RAM built in 13 or we're in trouble. Okay. Good, we're getting some things out of the way when we should be getting them out of the way. So here's where we're going up. You could work with the needles in this area, but I think I want to spread it out. I'm at 500 microseconds. I want it spread out a little bit more. So I think I want to go down in the unit to spread it out a little bit more. And maybe one more. Well, there we go. Okay. So that is one, again, you have to know how to play with these division things here. And then this is the old 63% when you're going up, 37 when you're going down. So here I am, I'm looking for the corner, what I call the corner when this starts to change. This is flat and then it just changed, okay. So here is, number one is at the corner. I'm going up to 5 volts, but I want 63% of 5 volts. 0.63 times 5 is 3.15. So I want this number 2 to be at 3.15. 3.148, that's pretty good. And so here is the time constant, 70.9 microseconds. Okay, that is L on R. It's supposed to be L on R. So let me just work in the crazy units I'm given. So 220 divided by 3.33 is 66. And that unit will be Henry divided by ohm will be seconds. And then I have 10 to the minus 3 in the numerator and 10 to the plus 3 in the denominator. So that's 10 to the minus 6. And so this is 66 microseconds compared to 71. So not too bad, though. We'll say that's the right ballpark. If we look at going down, as I say, this is me at my meanest. I missed it entirely. Oh, there it was. Okay, good. So now I'm looking for the corner. This is at 5. I'm looking for the corner. Looking for when it changes. It just changed. So that was the last time just before it changed. I need now going down. I want 0.37 times 5 is 1.85. That's where I want my second needle to be 1.85. 1.82, I'll take it. And this guy, now the time constant is, I'm getting simulation wise is 38. And we have to say that going down, I have R1 and R2 in series. So I add them. So what am I going to do? I'll divide. Let me clear. That's the first thing. I'm going to do 220. I'm going to divide that by parentheses 3.48 plus 3.33, close my parentheses, and equal. And there is 32.3, again, microseconds. And simulationally, it was 38. I might be able to do a little bit better if I stretch it out a little bit more. I might get a little bit closer, but this is good enough. All right. So again, so I'm telling you what I would do at my absolute meanest. I might throw a capacitor in series or parallel in the LC circuit. I might have a resistor that is in the, that's in the going up circuit, that's not in the going down circuit, or vice versa. That's the absolute meanest thing I would do on the RLs and the LCs. You're going to see them. You can set up the Excel spreadsheet ahead of time. You can bring it with you. Questions? is the last time you get to ask me a question in, at least for the recording. The one thing we didn't talk about was what a subroutine return. I'm stalling to see if anybody will dare ask me about the subroutine return microstates. Somebody already has, but asked privately and got feedback. All right. That either means that you're confident you got it right, or you haven't even tried, and so you don't even have a question yet. And you really should try. Otherwise, you don't have it, you know. You get better at those things as you try them. You start to see the patterns. Anything you want to ask me that's going to be on the recording? Room. Okay, we've gone. I think we've reviewed most everything. All right, I will call it there and hang out for people if anybody wants to ask individual questions. Stop recording.